A quick explanation of LeetCode 198, House Robber. So you are a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have security systems connected, and it will automatically contact the police if two adjacent houses were broken into on the same night. Given an integer array nums representing the amount of money in each house, return the maximum amount of money you can rob tonight without alerting the police. So this is a dynamic programming question, so hopefully you guys have a little bit of background or familiarity with the whole what's happening with dynamic programming. But essentially the gist is it's just using previously solved sub-problems to solve each problem. So this is going to be a really quick explanation, so it won't be super in-depth into how DP actually works, but essentially let's look at this test case here. So here, if we were to do a sort of run through or kind of just looking at the problem first, we can see that the answer should probably use this 60, right? It'll probably be, because we can't, if we use the 60, we can't use this 10, but it's probably a worthy sacrifice because 60 is so much bigger. But here, the answer would be 8 plus 20, so the answer would be 80, right? So using a dynamic programming approach here, we can store the answer to each sub-problem and then reference that answer later. So usually in the beginning, for the first one or two indices for dynamic programming problems, we just fill them in, and then for the rest, we iterate through. So first we fill in 2 and 7. So obviously, let's say, so for a dynamic programming, we assume sub-problems, right? So let's say this was our sub-problem. It stops at 2. So then the amount of money we can rob is $2. So let's say the sub-problem ends at 7. Obviously, we can't rob this house and this house because they are adjacent. Therefore, we just rob the second house because it's more money. So here's where the dynamic programming begins. At each step, so this is kind of our DP array, right? This DP array will store the answer for each subproblem from 0 to n. So it will store the subproblem from 0 to n. So when we look at this number here, we know that this house has $6. However, because we cannot rob this house to its left and this house, that implies that we can't necessarily just add 6 plus 7. So every time we reference this index, we have two choices. One, we can choose from 2 indices before, or so we can add, so basically we can add this value, the amount of money at this house, plus the answer from 2 indices before, or we can choose to just move this 7 over. And what we're going to be doing is we're just going to be choosing the maximum of these two. So if this array is the input array, then we're just going to be choosing, so at input I equals input I minus 2 plus, this is dp equals dpi minus 2 plus input at I, or it's going to just be dpi minus 1. And the reason why we can do this is because we know that this answer is already the max for this index, which implies that if we wanted to build a max answer for right here, one of our options would be to use this plus this value, right? Because they're 2 houses apart. They're perfectly 2 houses apart. And then the other option would be to just move this 7 over. You may note that this 7 here, we aren't necessarily going to be using this number at index 1. There are some cases where we don't use that number. However, we can still use the same thing still holds, right? Because even if you don't use that number, it's still valid to choose it. So therefore, we just use this formula the entire time and sort of build our DP array from that, and we'll see that the solution is eventually built. So sort of finishing off the run through, here we can see now over here 8 is best, now over here 8 is still best. It doesn't really matter which one we choose, right? Either way, the answer built is going to be the same, right? If we chose from this one right here, we don't have to necessarily, like you might be thinking that we have to store this first one's 8 over here, right? But we don't have to do that, because you might be thinking that, right? Because when we visit our next number, what if we want to use this number and we want to use this reference so that we can actually use this number? But it doesn't matter, right? Because we have it over here already. So we're going to be referencing it anyways. Okay. So we continue along. We see this is 18, right? 10 plus 8, or just bring 8 over. Obviously, we want to add the 10. And then we go to 60. 68 is way bigger. And then we chug along. 68 is still way bigger. So we keep 68. We completely ignore this 18 here. Very sad. And then we go to 80, which is our answer. And this remains 80 as well, because 4 plus 68, though it is 72, it is not as big as 80. So that is what our answer is. And so we just return the answer at the very last index of our array. And we can see if we did use our 4, what that path would look like is we chose this 4, we chose this 2, and then we chose, we chose the 4, and then we did not choose the 2. So we went straight to the 60 is what we did. And then we built 72 from that. But obviously from back here, we chose optimally, so we had 8 already. But yeah, that's all there is to this problem. Pretty straightforward, simple DP problem using subproblems to solve a bigger problem in linear time.